Okay, TD, that's how everyone calls me. So the motivation behind this whole Spark streaming as a research project was that we found there are many applications on the internet that actually has to process large streams of data and within kind of second scale latencies. I mean, you can see them all around you. There are check-ins, there are status updates that people want to filter spam from, the site statistics that you want to see, real-time statistics going on, the intrusion detection systems where you really need to figure out the intrusion within a few seconds, otherwise the whole point of detecting is lost. So, and these sort of workloads are not trivial. They cannot be run on a single machine. They really need a large number of clusters, a large number of nodes in a cluster to run because they're very CPU intensive. And as I said, they require latencies of few seconds, maybe not millisecond scale latencies, or maybe not minute scale, but second scale to be relevant, for the result to be relevant. So, and I'm going to use Conviva as the case study here. You've already heard from Jan what Conviva does. At one line answer would be it's in real time it collects metadata from online video sessions and shows statistics, real-time statistics on it. And for that they have a dual stack system. Correct me if I'm wrong. They have a dual stack system. One is they have a custom built distributed stream processing system which gathers all the data and computes thousands of complex metrics on millions of video sessions. Now this is very computationally heavy, and so actually it requires dozens of nodes to handle the processing load. It actually took many months to build and tune, etc., to get the required performance. The second system that they have is a Hadoop backend for doing the offline analysis of the same data that they have received, and to generate daily, monthly reports, to handle much larger volumes of data, to generate the reports. But what it essentially does is effectively pretty much the same computation that the streaming system does, except it needs it to be re-implemented in a different stack because Hadoop cannot do streaming and the streaming system cannot handle large data as Hadoop does. So that is what is lacking in today's systems, that there is no single framework using which you can build both kind of softwares, either streaming or batch processing that can handle large data. And it's obvious to whoever has developed these kind of systems is that it is actually really painful to maintain two stacks because you have to deal with idiosyncrasies and different computing models of two different stacks and try to fit them to make sure that the results that you get from both the stacks is same, etc., and individual bugs on two different stacks, etc. And the thing is that we feel that this is not a problem for only Conviva alone. This is a problem for a lot of different companies where you need to handle both streaming data as well as do an offline analysis on the same data. So this should be a common problem for many companies, and so therefore a problem worth solving. So the goals for this project was, one, of course, build a framework for large-scale stream processing that is scalable to large clusters, hundreds of nodes, and achieve near real-time latency, 1 second. Efficiently recovers from faults and stragglers, obviously because large clusters you will have worker nodes failing or some worker nodes being slow. And probably the most importantly that differentiates us from other frameworks is a simple programming model that integrates very well with batch processing as well as interactive queries. And existing systems do not achieve all of these goals together. Let's see why. So existing stream processing systems follow what we call a record at a time processing model, where there are a bunch of cluster nodes which are processing the data as they're streaming in. For each record that each node receives, it updates some mutable state in its memory and transforms the record and sends the record out to the next node in the processing pipeline. The problem with this model is that this mutable state it's actually very hard to make this mutable state fault tolerant, because if the node dies, all the mutable state on that node kind of dies, and your results may change based on some node dying. So to make this fault tolerant, there have been a bunch of techniques that has been in the past, like replication, etc., that people have tried to make sure that that this state is not lost, and even if a node dies, that state can be recreated, and the result does not depend on whether the node died or not. I'm not going into the details, but I will focus on one particular framework, which in this case is Storm, to highlight that what is lacking in existing frameworks. So what Storm guarantees is that each record that Storm processes will be replayed if one of the node dies and that node has not processed a record. So what it guarantees is that each record will be processed at least once. Not exactly once, at least once. So imagine you're maintaining a counter of counting the number of records you have seen over a period of time. That counter may be wrong because your one record may be processed, may have updated that counter twice, and you will never know. And so, and this mutable state can be lost due to failure, and your count maybe suddenly becomes 0. You have no idea why. So this is a problem. There has been improvements like Trident, which is built on top of Storm, that uses transactions to update state on Storm. But doing a transaction per state update is quite heavyweight, and that makes the whole that slows down the whole processing pipeline, because doing one transaction makes the whole thing very slow. By the way, feel free to ask questions at any point of time. And furthermore, they have no integration with batch processing models and cannot handle stragglers, slow nodes. There is no way to handle these things in these systems. Enter Spark streaming. The processing model, instead of record at time, what we use is what we call discretized stream processing, where the basic idea is take a streaming computation and run it as a series of very small deterministic batch jobs. The nice thing about batch jobs or batch computation models like MapReduce is that it can recover from faults and stragglers very efficiently. And because what they do is they take the job and divide it into a number of deterministic tasks. Now these tasks, being deterministic, they can be rerun if one of the node fails and some data is lost. Or if a node is slow, it can be speculatively rerun on a different node to get back the same result. Also, it can, if a node dies and some data is lost, those data can be recovered in parallel on other nodes by running by spreading out the rerunning of the task on other existing nodes. So fault recovery becomes faster because it happens in parallel. So the challenge is that we want to use the same recovery techniques except at lower time scales, at the scales of seconds, because we're dividing the whole data into batches of seconds. Now, the state between the different batches of data, the mutable state that I referred to here, is stored in memory as an immutable fault-tolerant data set. In this specific case, Spark's RDD that you already heard about from Josh. And because it's fault-tolerant, it is never lost. And I'll explain why in more detail soon. Now, to achieve low latency, the batch sizes can be reduced to as low as 1 to 2 seconds to achieve approximately 1 second latency. And since this is naturally built on the batch processing model, there's a potential to easily combine both streaming and batch processing workloads to bring a single unified stack that can handle both kind of workloads. That's the basic idea. Let's see underneath how this works. Let's say between time 0 and 1, you have received some input that input is stored on the cluster as a distributed collection. In this case, it's an RDD, and it is replicated in the memory of all the machines so that it is fault tolerant. Now you apply the standard batch operations like map and reduce on this data set and create a new data set. Now this new data set can either be the output data of the final processing, let's say counts of the records that you received, or it can be intermediate state data that you will be using again. And if it is an intermediate state data, then that data will be stored in memory again as RDD, which are distributed by definition fault tolerant. And then when the next batch of data comes, the state data is combined with a new set of input data, and the next version of the state data is generated. And so these different versions of the state data forms basically a state DStream, and of course the input data is basically an input stream. That is the high-level model of how this discretized stream processing works. Any questions? Yep.
What's the difference graph here, it's just like the Spark.
It is like Spark.
Yeah,
so
there's
all
no. My understanding is from this slides. I didn't see any special for streams. It seems that you dump the stream to a distributed file system, and then you feed that into the Spark, and then one state in memory, and then feed that to the next operator, and then still keeping RDD for more. And then finally you want to proceed to the distributed file system or not. But what's the streaming components in this?
So the
What's
question.
the difference between the streaming Spark and the Spark?
Streaming Spark. So the question is that what is the difference between streaming Spark and Spark, because you're doing the same RDD operations that Spark does. That's a question at a high level. So and the answer is there is not much of a difference. What we provide is we're doing underneath the same Spark, the same RDD operations, except what we provide is a streaming abstraction on to make this doing all the management of time, the processing of data, seamless and easy to program for someone who wants to write a streaming program rather than a standalone Spark program.
Let me put this way. So if let's say my interval to collect stream data is every 10 minutes. So I create a file on your distributed file system with a timestamp, let's say February 1st, 9 a.m. This is 9 a.m. 0 minutes. And then I create another distributed file folder, contains the next batch, and it just batch all the stream data into the distributed file system, and then Spark process them in the temporal order of the folder. And that's
what will be the latency for that?
It's your Spark ability to digest the folder by folder. Is that?
But you need to store on the disk, right? And you need to read from the disk.
Yes.
So he is.
But this can read from like a socket.
Here, the graph shows the input is stored on a distributed file system.
No.
It's memory. I see here.
It's memory, and it has been received from the network, from any network input source. It need not be HDFS.
So you stream into the cluster,
Yes.
and then the operator take them
Yes.
one by one.
Yes.
And okay, so you handle this in streaming. I see. Okay.
So that's how you can achieve second scale latencies, even sub-second latencies. If you keep continuously write to HDFS, I don't think you can achieve second scale latencies
So if
using
you
that.
stream arrive faster than you digest the speed, you batch them in the memory.
Sorry, could you
So
repeat?
if the stream data arrives faster, so let's say 1 second you can consume 1 gig of data, and then the arrival rate is 2 gig per second. Do you handle that?
You need to have multiple receivers receiving it or a larger cluster to receive and process the data. Or you could adjust the batch size. For example, what you've seen is as you change the batch size, the throughput of the cluster increases depending on your workload. So you can adjust the batch size to allow to process.
Speed, I see.
Yes. So there are knobs that you can control to handle your data loads, processing loads. Yes.
So the problem is like because the input is not it's not a constant input, right? It's dynamic one. How do you know? Well, sometimes your system is underloaded, sometimes it's overloaded, right?
That is a very good question.
And also, you don't know your task in the for the computation, right? You can have ad hoc task there, and it's not fixed, right? How do you plan your system, right?
So right now the size of the batch is fixed. So it is important to set the size of the batch a priori before starting the system based on the load that you expect. But these are some of the research ideas we are dealing with, that how can the system automatically figure out what is the processing batch size based on the current load of the system. So the question is that how do you figure out what the load of the system is and whether the batch size that you have set will make the system be overloaded or underloaded. That is a very good question.
So this is a fundamental question with any streaming system, right?
Exactly.
So you get data coming in. What happens if you don't have enough resources to keep up with the data? And there are only two possibilities. You delay, you fall back, or you shed the data. You throw away some of the data.
That's it.
Yeah.
You know, it's so this
So
one
which
you are
one
going
are you doing right now?
to fall back, but
Which
you
one
can
do you
imagine
like?
as we discussed. Also, you can potentially throw away the data.
So which one do you guys use?
You are going to fall back in this case, right?
Yes, we are going to fall
And
back.
that's going to be delayed, to increase the delay. And
DQ
if the load decreases, then you are going to catch up.
DQ it somewhere, or so you don't consume it like
Yes, you don't consume it.
Yes.
Okay.
Yes.
You can put a queue in front of this if
Yes.
you want to.
Rabbit
Yes.
MQ or
So you can implement your own sampling algorithm based on the processing load. So for example, if you're queued up, then you can basically shed part of the data depending on how queued up you are. This abstraction allows you to do all that optimizations underneath.
So again, by default, you are going to fall behind, but you can shed the load or process only subset of the if you wish.
Yes, but there are a number of questions. Can you hold your questions?
I can hold my question. We can talk later. Yeah.
Okay, thank you. Can I ask you to hold your question? Thank you so much. Good. So the way the system recovers from falls is that because they are stored as RDDs, they are deterministically recomputable. And so if, let's say, you had a state data that is stored in the memory, but it is not replicated, but the input data is replicated, and one of the node dies, part of that state RDD is lost, some of the partition is lost, that can get recomputed in parallel on the other nodes, thus allowing you fast parallel recovery of data without the cost of full data replication of all the intermediate data that you have. Let's talk a bit about the programming model that we provide that makes this whole abstraction of programming against a stream makes it very convenient and very similar to a batch programming model. So the abstraction that we provide is a DStream, which is basically a series of RDDs representing a stream of data. And the API that you have seen is for RDDs. The API for DStream is also very similar. And these DStreams can either be created from some live input source or by transforming other streams using map, reduce, and the standard operators. So the DStream data sources that we provide out of the box in the alpha release is, we have quite a bit of sources. There is plain old HDFS, there is Kafka, there is Flume, there is a source for taking Twitter data, there is plain old TCP sockets. You can take your arbitrary data from TCP sockets. And there has been two more sources that has been contributed by external developers, Akka, Actor, as well as ZeroMQ. And the API says that it gets easy to add your own because the developer came up with this within a few days of playing around with the API. Now, what can you do after you create a DStream from a data source? You can basically do a transformation where you build a new stream from existing streams, and you have RDD-like operators that you saw, like map, flat map, filter, or group by key, reduce by key, join. What you also add is a new set of operators called window-based operations as well as stateful operations, where you can do operations over a whole window of data, or you can maintain arbitrary state and keep updating that state based on new input data, which gives you the whole streaming abstraction that as new data comes in, you update your state. And I'll explain this soon. And finally, after you transform all the data, what you can do is send the data outside, either save it to HDFS or some external database using output operations. And we have a number of them, like save as Hadoop files, or the very generic for each, where you can give it an arbitrary function that takes an RDD of data and does anything with it you like. You can push it into Cassandra or whatever way you want to play with, get the data from the RDD outside your cluster. To better explain what this DStream API allows you to do, let me go through an example and let's say we want to process a stream of tweets to find the 20 most popular hashtags in the last 10 minutes. And I am going to basically break down this problem into 4 steps. First, get a stream of tweets from Twitter and isolate the hashtags. Second, count the hashtags over a 10-minute window. Then sort the hashtags based on their count. And finally, take the top 10 or 20 hashtags. Okay, 20 hashtags. Here goes. Step 1, create a DStream from Twitter. You give it your username, password, and it creates a tweets. This is basically a DStream. Second, we use the flat map operation to extract out the hashtags from each of the status updates in the tweets DStream. And this creates a new DStream, and flat map is obviously a transformation, creates a new DStream hashtags. And what happens underneath is that as time goes on, you receive tweets from Twitter. They are formed RDDs, and each RDD is basically the operation flat map is applied to generate the hashtag RDDs. This is what happens over time for each time step. Second step. Now that we have a stream of hashtags, what we want to do is basically count them over a 10-minute window. And for that, what we provide is a simple operator called window, which basically does a sliding window operation, which aggregates the data over 10 minutes and does a standard word count like map reduce on them to find the counts of the different unique hashtags. And what happens underneath is this. This is the stream of hashtags, one RDD for every time batch. And go over a window, all the hashtags are aggregated together and reduced finally into the final tag counts for that particular time. And as the window slides, this thing is done again over the new set of data in the window. Well, this works for any arbitrary window-based computation, but not the most efficient one for counting, which is what we want to do. So we provide a higher level abstraction called count by value and window, which basically counts the number of unique values over a window. And why this is more efficient, let's see what happens here. Here we are processing each batch of data multiple times for each window, which is not very efficient. What you can rather do is take the hashtags, reduce them individually on a per batch basis, and take the window over the reduced values, and then reduce them further. And this reduction can be done in a completely incremental fashion, where you take the values that you had in the last window, add the new reduced counts that got added to the window as the window moved, and subtract the counts that got eliminated from the window. And this incremental computation is much, much faster than processing the whole window over and over again. The key thing to note is that this required an additional function called subtract, which allows you to kind of inverse reduce. And using that, and that concept can be basically extended to any generic reduce functions which has an inverse function associated with it. So you can, yes?
You go back to a previous page.
Yes.
So that each block is one RDD?
Yes.
So it corresponding to one unit of data?
It is one parallel collection of data.
So how do we enforce the 10 minutes window?
How do we enforce?
How do you enforce, right? So how do you know, like, you enforce the timestamp moved 1 second, you remove the past few seconds away?
Yes. So basically we maintain indices based on that this was the data received for this particular timestamp. And so whenever we move the window, we take the reduced values corresponding to time step t-1 and subtract those values with the final counts of the previous window.
So you do per second or what unit did you do, right?
Per second or per batch size, whatever batch size you specify.
You tell it how to advance in there. You say the size of the window, which is 10 minutes, and the advance,
So
which
you
is 1.
balance it.
Yeah, so you can tell.
Simple question on this. The timestamp is from the time the streaming server receives it, or can we add the timestamp like further forward in our stack?
In the current implementation is based on the wall clock time of when the system received that particular record. So, yes, that's the current implementation. Yes?
So can you give different weights? For example, T has weight 1, T plus 1 has weight 1.
Yes, absolutely. You can implement your own custom windowing to do any kind of window-based operation. actually, I'll talk about an application where one of us actually has done that operation. So you could have been, and so do you have a question? No. Okay. So we provide this generic interface for doing arbitrary invertible reduce, and you could have done the counting basically using that as well by specifying the add and the subtract functions, like this. Third step is basically, and I'm going to go through this fast because we're running short of time. We basically want to sort the hashtags based on the count. So we do a map step to flip the key value pairs because we want to index by the count now because we want to sort by the count. And then transform is a function, a DStream function that allows you to do any arbitrary RDD operation. So in this case, we are doing we're calling an RDD operation called sort by key, which sorts the RDD, sorts each RDD that is present within that DStream. And you could use this to, let's say, take a DStream and join it continuously with some HDFS file. And so basically you have a stream of tweets coming in, you have a file which has spam hashtags in it, and you want to filter the spam hashtags continuously on the tweets. You could have done something like this using this transform function by joining it with the file, which can be stored in memory, of course. So this allows you to combine stream computations with arbitrary batch computations because you can combine both DStream and RDD operations hand in hand. And the same scheduler will do both sort of operations. And then and this will give you the final sorted tags for each batch of data. And then for each tag, and then finally we have the foreach function, which takes each batch of sorted tags and shows us the top 20 tag. I've just used a simple function to explain that. And this is the output operation that I run. And this is the final code. It's not too big for something that you want to do. And let me show a demo of this code actually running. That all the code that I've showed is actually code and not pseudocode and pie in the sky. And this is actually the program running. Hold on. This is the actual program that you saw, Twitter stream, etc. There is some more boilerplate out here. Similar to Spark context, you need to create a streaming context, which gives you all the functionality like create a Kafka stream or a Twitter stream or a file stream. And so you create the streaming context. What I'm doing out here is I'm going to run this, it's actually running on a cluster of 5 machines. So what I'm doing is I'm creating 5 Twitter streams out here and doing a union of those to combine them into make a single stream. And then whatever you saw, tag counts, sorted tags for each, I'm going to show the top tag. And this is actually running, but to show that this is, I'm going to start them again. Yes. And so since it's a 10-minute window, it will require a bit of time to aggregate enough data to show the 10 things. A better way to see it would be on the browser. This is the top 20 tags in the last thing. And let's verify that I'm actually running real Twitter. Some of these tags may be visible on the Twitter website. Let's see. The Twitter website says that the current trends, let me refresh it, is something Tengo que and vivimos un país donde I don't know Spanish. Vivimos un país donde tengo que
reconocer que.
Yeah, okay. Sorry if I spelled it wrong or it was a curse word. I have no idea. So this kind of shows. I hope this proves that I'm actually running it on a live Twitter stream. What? Okay. Yes, back. So the other operation that I would like to highlight is that you can use this to maintain arbitrary state. Let's say you want to maintain for each user based on its tweets that that he or she is tweeting the mood of that user. and so you want to continuously update that mood as he or she is tweeting, you could do something like that. I know that sounds very creepy, but suppose you want to do that, and so for that for every input that you receive in batches, you basically take the previous state, update the state, and create a new RDD, and in this way you can make a stream of states. What you can also do using DStreams is, if you run DStreams from a Spark shell, you could actually ask the DStream that give me this slice of data from this time to from this time to that time, and then use that to run interactive queries. And so that will allow you to combine streaming, batch, or interactive queries all using this same single API. Some numbers about the performance that the whole streaming system can achieve. We ran basically a grep workload where there are 100 streams of sentences that are 100 byte sentences that are coming in on 100 nodes, and you want to grep them together to find, as you can see that as the number of clusters in the node increases, the throughput of the system increases linearly, showing that the whole system scales. In total, it can process 6 gigabytes per second. At 6 gigabytes per second, which is total 60 million records per second at sub-second latency. And similarly for word count, you can see, again, it also scales well. To compare with Storm, and I think this is one of the things that people it's on their minds, we have found that Storm, based on their architecture, is limited by the number of records per second it can process. And in our benchmark on 30 or 40 nodes, Storm was, we ran the same grep and word count workloads and using 100 byte or 1000 byte records, and we found that Storm was limited to 115 records per second per node, while we achieved 670K records per second. Apache S4 we also tried, that had much lower performance. So yes.
For Storm, was this with the exactly once computational semantics at Trident?
No, this is with the at least once. Okay. Very good question. Yes. And I've heard from developers that getting that exactly once has a very, very significant performance hit, that so many developers actually turns it off. Yeah. They don't want it. To show that this you can recover from false and stragglers fast, here is the time taken to process each batch of data, and a system failed. One of the worker nodes died, and it kind of recovered really fast. It took just one batch took slightly 1 second more, but it recovers really fast from the system. Some more stuff about Conviva, otherwise people are going to beat me up. So last summer I did an internship in Conviva where we basically tried to see whether a real application like Conviva's streaming application can be implemented on the Spark streaming and the required performance can be achieved or not. So for that, what we try to do is take their Hadoop stack, Hadoop jobs, and try to run it on Spark streaming. For that, I implemented a wrapper that allows Hadoop jobs to be run on Spark streaming. We call it Shadoop, for the lack of a better name. And we actually ported the Hadoop part of Hadoop stack to run it on Spark streaming, with a lot of help from folks out here. And we could actually achieve linear scalability with 2 second batches, about 3 second latency, and process millions of video sessions, much more than their system has ever experienced. And so real system actually works on Spark streaming. Sorry? Okay. Another real application that we tried on Spark streaming was we have this project in UC Berkeley called Millennium Project, where people use GPS observations to estimate traffic transit times using machine learning. And they use really complicated algorithms like Market Chain Monte Carlo simulations on this GPS data, which are very CPU intensive. Therefore, to process substantial amount of data, you really need to have a large cluster. And we ported that to work on Millennium Project, and that also scales linearly. A final sentence about the failure semantics. Since input data is replicated by the system, if a worker node dies, your data will be recomputed, as I've said. All transformations have exactly once failure semantics, because all because the RDDs by definition are deterministically recomputable. The output operations have at least one semantics, because if a task doing the output operation dies, the task will be relaunched again. So even though the data that it may write to an external storage may be the same, it may be written twice. So for example, if you want to save to HDFS, the same file will get stored twice, which is probably fine. But if you want transactional guarantees, that is something you need to implement within that for each function or arbitrary output operator that you need to write. So that's one. We also have a Java API for streaming already, and it was developed by Patrick, who unfortunately isn't here. It is also similar to the Spark Java API. So for both trying Spark and Spark streaming, you really don't need to know Scala if you already know Java. Finally, this project already has seen a number of contributors. Most importantly, already there have been 3 external contributors who has contributed code and examples to it. I don't think I have time to walk through that. Finally, the vision that we want to leave you all with is this, that if you have a one stack that can handle all kinds of workloads, it becomes very easy for your productivity. Because let's say you are an online social network, and you're finding that people are reporting about new kinds of spam, and you have no idea how to find that or filter that spam. So you take some logs, and interactively using the Spark shell can figure out that, okay, this is the right set of algorithms or the filters that you can use to filter this new kind of spam. Now, once you've written that algorithm inside the Spark shell, you can take that same code and run it on a much larger data using a Spark batch job. You don't have to rewrite that algorithm again on a different framework. And now that you've perfected the algorithm on a much larger piece of data, you can stick that same algorithm onto your streaming system, implement a Spark streaming. So you don't have to re-implement the algorithm again. And so you can very easily get the spam filtering on your stream processing system. So that having a single stack to rule all your data analytics needs gives you that power and simplicity. Yes?
So the interactive shell matching that you do for Spark
yes.
Batch jobs, you do the same thing for your streaming jobs?
Technically, yes, you can, but it's probably, I don't know whether it's a good idea, because you want the Spark streaming system to run 24/7. You usually don't do it. But technically you can, and in future probably we're going to add more support to it to do something that more conveniently. Right now for the alpha release, the support is minimal. Just to end, before ending, we are doing, I don't know how many of you know about the Strata conference. We are doing a 2-day tutorial on Spark, Shark, and Spark streaming. This coming Tuesday and Wednesday. I think if you're interested, you should definitely see that and come and see our talks. And most importantly, we will be doing a hands-on tutorial that will actually allow you to learn how to use these 3 frameworks. That's part 2 on Wednesday. To conclude, this is
They're both on Tuesday.
they're both on, they're both on Tuesday.
Yeah.
Good. Finally, the alpha is going to be released 3-4 days, as Mati said. Look at the new Stream programming guide if you want to play around with it. If you want to know more about the paper, that's the URL. And thank you.
How do we stream data from Flume Avro sync to Spark?
We have something called, just like TweetStream, we have something called Flume Stream that plugs into Flume, and so you can do that very easily. That support is already there. Any other questions? Yes?
Yeah. Are you going to reach a point where you can specify the time of events not at the collector, but inside the data being sent?
That is something we have been considering for a while. We hope to do that in some of our future releases.
So just to answer a bit on that, you can do that a little bit at the application level. So you can say group by and group them by the external timestamp field.
Yeah.
And then you have to decide, like, at a certain real time, do I think I have enough events for a certain, like, time they happen. So that, later you might see them. But you can use a group by to do that.
Yeah, it's possible. You just have to compute sort of an error window of, this
Yeah,
event may have
exactly.
been in the past few hours.
Yeah, so that's kind of, and we might include that in our API and translate it to something like that underneath. Yeah.
Thank you.
What's the process like? So say you have a job running and you update the code. What's the process for redeploying that? Do you have to stop the existing job?
Yes. Currently, that's how the system is designed. You have to stop the existing job. It cannot be updated incrementally. Yes.
If there's a streaming job running and you have buffered some data in memory because that's more load and you want to let the system catch up by itself.
Yes.
Is that since the data is in memory, what if that node goes down?
So because the input data is replicated on multiple nodes, if one of the node goes down, that data is still there on another node.
So what is so I guess the next question in my mind is, at what rate would you replicate the input stream data across nodes?
The rate at which it can maximum handle. So you're limited by the network bandwidth.
Okay, but that's not something you configure when you create the context too.
Not right now,
okay.
But that is something that people have asked for, so we might include that kind of a feature in future releases. Okay. But that is something that people have already asked for.
Thanks.
Yes.
So in kind of addition to that, what's the replication factor?
2 by default, but you can set that using any by specifying a custom storage level. That is very easy to configure. Yes. Yes.
Is the batch size, you had said it's set, is that set at the cluster level or at the job level?
At the cluster, at the whole streaming app level. So when you create the streaming context to do all your computation, you specify the batch size over there. Okay, thank you.